In this video for VCE Algorithmics students, I go over some features and variants of the graph coloring problem and its time complexities, then show various ways of solving it, including backtracking and simulated annealing. For all variants of the graph coloring problem, our aim is to color the graph so that no adjacent nodes have the same color. We might want to see if this is possible with 2 colors, 3 colors, or 4 colors, or we might want to work out what is the minimum number of colors needed. The decision problem requires us to work out whether or not this graph can be colored with n colors, and the optimization problem wants us to work out the smallest number of colors needed to successfully color the graph. The naive approach requires us to generate every possible combination of colorings with a given number of colors and then see if they work. So we start with 2 colors and we generate every possible coloring, which means that each node has 2 possibilities. For each node, we have to consider the possibilities of the next node and so on, giving us big O of 2 to the power of v. For each coloring, we have to check for conflicts that we might do using depth first search, which is big O of v plus e. After that, we will try 3 colors, which by the same argument gives us 3 to the power of v. Now, all planar graphs, like the ones shown, can be colored with at most 4 colors. A non-planar graph may, in the worst case, require 1 color per vertex, giving us a worst case for the optimization problem of big O of v to the power of v, which is very bad. So just to quickly summarize those time complexities, for k colors, k options for each of v vertices, we have big O of k to the power of v. For unlimited colors, it could be big O of v to the power of v. We'll consider the problem classifications. We know that the decision problem is NP complete. It's at least as hard as any problem in NP, but a solution can be verified in polynomial time. We just need to check to see if the proposed coloring has any clashes. The optimization problem is NP hard and not NP complete, because even if we're given a solution, the only way we can check that it's the best solution is by making sure that no other solution exists, which means doing the search again. And this is how the problems fit into our Venn diagram of problem complexity classes. How does backtracking help? Well, it improves the time complexity by pruning the solutions we know that can't possibly work. So with the naive approach, a lot of these solutions just could not possibly have worked. So, for example, on the top left, once we have 2 adjacent red nodes, there was no point in generating all the other ones, so that was wasted time. We're going to use backtracking to prune the rest of those and go and try the next possible solution. To do this, I generated some code using Grok, because that's what we do these days apparently. We're going to step through it, see how it works, indeed if it works, which is an important skill if you consider yourself a vibe coder. This is what Grok believes a vibe coder looks like. Let's start. Note the helper function here. It's fairly self-explanatory. It checks to see if a particular vertex can be colored with a particular color. Next, we have 2 functions. The top one is the driver function, which calls the bottom recursive function, which is the one that does all the main work. Now you can see the way Grok generated this used a graph object, which I removed on all except one of the last lines, which I forgot to. I'm numbering the vertices because the way the function is set up, we consider an array of size the number of vertices. So we're going to imagine this is an array where all the vertices are in order, but that's not the only way of doing this. We call the color graph function, and we're just going to step through that. The first part, it's a recursive function, so we have the base case, which is easy to see once it's been written, but when you're writing a recursive function, it's always easier to do at the end. So if we find the vertex number is the same as the number of vertices on the graph, then we say, well, we've colored it, it's all worked out, so it must be true. Then we're calling this on vertex number 1, which we'll keep track of in the blue box there. And we check to see, is it safe to color vertex number 1 red? I'm going to use the colors 1, 2, 3 to correspond to red, green, blue. Hopefully that's memorable enough. So we've said it's safe to color that red, and so we color it. And then we check to see if vertex number 2 can be colored using red, which of course it cannot. So we go back and we try coloring it green, which it can be. Now we move to vertex 3. We say, can that be colored red? Yes, it can. And we can start to pick up a bit of speed with this. We go to vertex number 4. Can it be coloured red? No. Green? Yes. Vertex number 5. Red? No. Green? No. Blue? Yes. Vertex number 6. Red? No. Green? Yes. We get to vertex number 7 and we find it can't be coloured red or green or blue. So we have to reset the vertex colouring back, and we have to take a step backwards. We go back to vertex number 6, which was already coloured green, so we can only try one more. We can try blue, but of course that doesn't work. So we recurse again backwards, and we have to go to vertex number 5. Vertex number 5 was blue, so there are no other options there, so we have to go back to vertex number 4, which was green, so we colour that in blue. Okay, you get a sense how this works. Now, the actual solution to this, I mean, we can see that vertex number 7 is the problem because it's connected to vertices which all need to be pretty much different colors. So we're just going to step through quickly, and as we can see that 7 won't work as is, I'm going to try and set vertex 7 in the first place. So we're going to start here. 4 is red, 3 is green. This is just me speeding up the process for the video. Although it introduces some ideas for the heuristic. We might start with edges that have higher numbers of, like a higher degree, and use that to colour the other edges because they've got more flexibility. So once we get to this point, we can see this probably isn't going to have a solution. So I'm going to take out an edge, and just to demonstrate how this returns the function, we get to vertex number 8 and we can colour it red. Then we consider vertex number 9. So we call colour graph on vertex number 9, which can't be coloured red but can be coloured green. So now we are calling colour graph on, now it says vertex +1, but because of the 0 indexing, this is what is going to kick in. We're actually probably going to be working on the value vertex here is actually going to be 8. So when we do +1, we've coloured this into 9, and 9 is the number of vertices, which means we are going to return true. Now this is something where I thought the Grok solution wasn't very good, because they rely on the variable colouring to be a global variable which isn't passed back up through the recursion. Now you could do this, but I'd say it's much safer to say, well, we're going to return the colouring at each stage. That gets passed all the way up through the recursive calls and gets returned to the original function up here. So with backtracking, we can see it still takes a long time. We still have lots and lots of options to try, and I suppose in theory it could be that we have to try just as many options as normal. So the worst case time complexity is technically the same, but we would say something like, well, it's going to be quicker in a general sense. Next, we consider simulated annealing. Now, this is different to backtracking. Backtracking will still find the best solution. Simulated annealing is a much quicker heuristic for finding a quite good solution, or at least a solution we hope is quite good. It works on the analogy of cooling metal. So we start with a high temperature, and that temperature goes down with time. And we're just going to have some very high level pseudocode here. We generate a random colouring, and then we measure the conflicts. So each one of those can be done in poly time, and these are highlighted here. You can see there are 4 conflicts, and then we make some kind of change. Now the change could be random, or we could change the vertex that has the most conflicts. That would be quite sensible. We make a change, and note at some point the temperature goes down. I've changed that vertex up the top, highlighted in yellow, and then we measure the conflicts again. This time you can see there are only 3 conflicts. That's less conflicts, fewer conflicts, so we're going to keep the change. Let's see what happens on the next couple when we get to more conflicts. So we're going to continue. The temperature has decreased again. We're going to make a change. We're going to change this one, count the conflicts, and I think I set this up so it's now worse. We're back to 5 conflicts, and we're going to roll the dice and see how the dice roll compares to the temperature. If the dice roll is below the temperature, then we are going to keep that change because we hope that globally it might lead us to a better solution. So you can see as the temperature goes down, the probability of accepting that dice roll goes down as well. So we make another change. We're going to change this one. Measure the conflicts. Fewer conflicts. I think we said we'll keep that. Make a change. Measure the conflicts here. I think I've made this one deliberately bad, so this one now has 7 conflicts. We roll the dice, but in this case, the temperature has gone down and the dice roll was unlucky. So we are going to discard that change, go back and do something else. And then we are just going to keep going. We want to continue until either no conflicts or until a certain temperature or time is reached. Now, if there's no solution found, we could then say, well, it didn't work with 3 colours, let's try with 4 colours. Depends a bit on the context. It might be that an imperfect solution is okay, because if you were doing some kind of scheduling problem and you've got 2 conflicts, it might just mean there's 2 people who can't do those particular combination activities or whatever it is. I'm thinking about a question from a couple of years ago where you were scheduling members to attend certain gym classes in certain rooms. When you're writing your explanations for simulated annealing, by the way, one of the biggest mistakes is to only talk about simulated annealing in terms of temperature, better or worse solutions. So if we were talking about a scheduling problem, we would say randomly change one of the whatever the scheduling was, like a timetabling block or something like that. It really depends on the context. And yeah, don't just talk about temperature and better or worse solutions.